Hello there. Today's video lecture will give a start on the term limits, which we start as a beginning intro to the section of derivatives. Limits is a section or an area which you have dealt with while you were doing your high secondary. And as a recap, we'll see how we define limits in this lecture. Usually we denote a function in the positive x-axis and y-axis like this. This is the positive x-axis. This is a positive y-axis and you have a function like this, right? For every point in lying on the x-axis, you have a corresponding point on the y-axis associated with it. For example, suppose if you have an x here, the point x is on the x-axis, then the corresponding functional image will be f of x, and you write the point here on the function denote it as the ordered pair x comma f of x, right? So, talking about a function and its limit of a function at a point. So, suppose you're taking a point x naught here, okay. The limit of a function f of t at the point x is equal to x naught at this point is the value which the function f of x approximates when x is moving close to x naught. That means, see, when we are approaching this x naught from the right and from the left, okay, how does the value of the function change? How does it move? So here we know that when the value is moving towards x naught in the x-axis, here the function is moving like this from the left and the function is moving with the values from the right like this, right? So that means the function is moving to somewhere here, right? So that is an illustration with the help of this example. If the function is this, the functional value is happens to be on this curve, then that's how we can illustrate what a limit is. So the limit of a function f of t at a point x is equal to x naught is the value which f of x approximates for x moving close to x naught. So in this section we are introducing limits and their properties, and to set a better illustration, let's look at a function. Okay, the function we are going to look at is 2x square minus 7x plus 3 divided by x minus 3. This is our function. Okay, you can observe the denominator and see that if x is taking the value 3, the denominator will be equal to 0 and this fraction cannot be determined. Okay, so we are always excluding such a value x in such situations. That means we never take the value 3 in such situations. So we conveniently take the domain of the function f to be equal to set of all real numbers. This function, the x in the function can take any real number value except for 3. So we write it as the set of all real numbers. We denote it as script r minus, and it is in a slanting form. That means we are going to exclude the set 3 from the set of all real numbers. So what we are going to do in the next step is that we are going to calculate some values of x near this 3. We said that 3 doesn't have the corresponding functional image because the denominator is going to 0. We are going to find the values of the function for x really close to 3. Okay. So suppose if x is equal to 3.5. Okay, you're calculating 2 into 3.5 the whole square minus 7 into 3.5 plus 3 divided by 3.5 minus 3. When you calculate, you get the value 6. You can use calculators, your scientific calculators, and find it out to get 6. And in the next step, we are going to consider 3.1, which is also close to 3. So 2 into 3.1 square minus 7 into 3.1 plus 3 divided by 3.1 minus 3. When you use your calculator, you can see that it is 5.2. Okay. The next one is 2 into 3.01 square minus 7 into 3.01 plus 3 divided by 3.01 minus 3. You get it to be 5.02. Similarly, you calculate for 3.0001, which is also very close to 3. You get simultaneously the value for f of x to be 5.00002. Also 3.000001, you get the value 5.000002. Okay. So you can see that these are values to the right side of 3. Now we are going to look for values to the left side of 3. So for that, you first calculate the functional value for 2.5. 2 into 2.5 the whole square minus 7 into 2.5 plus 3 divided by 2.5 minus 3. You get it to be 4. Then calculate for 2.9. You get it to be 4.8. Then 2.99. You get 4.98. 2.9999, you get 4.9998. 2.999999, you get 4.999998. Okay. So from all these, you can see that when we approach 3 from the right side or we are approaching 3 from the left side, the corresponding value of the function always is approaching to 5. Here see, you are getting 5.000002. That means it is approaching 5. Here it is approximately moving towards 5, right? So as x gets closer and closer to 3, f of x gets closer and closer to 5. That is, f of x approximates 5 for x close to 3. So how does it is it is represented as limit x tends to 3, f of x is equal to 5. You will see how it is represented later on. I'm just mentioning it earlier. This is how we represent it here. So as in a discussion of the derivative, it does no good to set x is equal to 3 because we cannot set x is equal to 3 because that value we cannot define f of x. So you note that here f of 3 is not defined here, but the limiting value of f of x at 3 is 5. So this is an important note for this example. Note for this example is that f of 3 is not defined, but the limit f of x as x tends to 3, 5 is equal to 5. We have calculated it. Now, in this case, we know that our function is 2x square minus 7x plus 3 divided by x minus 3. In order to make our make steps easier, you can just factorize this 2x square minus 7x plus 3. How do you factorize? This is a quadratic form, right? So you take the product of the first coefficient of x square and the constant. That means 2 into 3, that you get 6 plus 6. And then what you do, you take the coefficient of the term x, that means that is minus 7. So you have to find factors of 6 such that the factors add up to get minus 7. So you know that that will be minus 6 and minus 1, because minus 6 into minus 1 will be plus 6, minus 6 plus minus 7 will be minus 7. So all are satisfied. So this is the product, this is the sum. That is how we calculate, right? So you get from there, you can get 2x square minus 6x minus x plus 3 divided by x minus 3. You are factorizing it. You can take 2x out, so you get x minus 3. Here also x minus 3, you get a minus 1 here divided by x minus 3. So you get x minus 3 is a common term into 2x minus 1 divided by x minus 3. That's how you get this. And from that, when x is not equal to 3, you can cancel out x minus 3 and x minus 3 to get 2x minus 1. And at x is equal to 3, x getting close to 3, thus 2x minus 1 is approximating to 5. Okay, so suppose we have a function f of x and we are interested to get the behavior of the function near some value x naught. Assume that f of x is defined for all x near x naught, but not necessarily at x is equal to x naught itself, like we said in the example. So if the value f of x of f approximates to a number L as x gets closer to a number x naught, we say that L is the limit of f of x as x approaches x naught, or f of x approaches L as x approaches x naught. So there are two notations for that, for the same. We said it earlier during an example. One is f of x tends to L as x tends to 0, or we can write limit x tends to x naught, f of x is equal to L. So in the example, we wrote limit x tends to 3, f of x is equal to 5. So in general, we are calling that as the limit L, and this x naught is the arbitrary number instead of this 3. Okay. So in the example which we discussed earlier, we can write either like this, that is, this is the f of, this was our f of x, right? This is our f of x we mentioned. So f of x tends to 5 as x tends to 3, or limit, so this is f of x, or limit f of x is equal to, limit x tends to 3, f of x is equal to 5. So either way you can write, we always prefer this. Now let's see the example 1. Using numerical computations, we have to guess the value of limit x tends to 4. This x tends to 4, the fraction 1 by 4x minus 2. So as we did earlier, we are going to make a table. We are going to uh, find the values near 4 to the right and left. Okay, so 4.1, 4.01, 4.001 are the values to the right. We are taking values to the right like that, and values to the left as 3.9, 3.99, 3.999. Using your scientific calculator, you can calculate 1 divided by 4 into 4.1 minus 2 to be 0.0694 and calculate each of them to get simultaneously all these values. And when we are closely looking at the values we get for the function, you can see that the function is moving close to 0.071. See, it is moving like that. So in addition, we may notice that as x tends to 4, the expression 4x minus 2, or we can say that 4x minus 2 in the denominator of our fraction is approaching 114. If we observe it very closer, you can understand that. That means the value limit x tends to 4, 1 by 4x minus 2 is equal to nothing but 1 by 14. So you can guess it out by putting 4 here, right? So we are going to officially define what limit is and what is its notation. If the value f of x approximates the number L for x close to x naught, then we say that f approaches the limit L as x approaches x naught. Nothing. It is very simple. That means when x approaches to x naught, so from right and left, f of x approaches to some number. So this number is called limit. If it approaches, that number is called the limit. And we denote it as limit x tends to x naught f of x is equal to L. So there are some remarks or notes we have to keep in mind. Limit x tends to x naught f of x depends upon the value of f of x for x near x naught, but not x equal to x naught. We are not, it is not always necessary that limit x tends to x naught f of x is equal to f of x naught. Like there can be cases like this, there can be cases like this. According to our functions and points, this can happen. That means limit x tends to x naught f of x not equal to f of x naught can happen, or limit x tends to x naught f of x equal to f of x naught can happen. Anything can happen. Indeed, even if f of x naught is defined, it can be changed arbitrarily without affecting the value of the limit. So even we can reconstruct our function. If already f of x naught is defined, we can even reconstruct that function without the limit getting affected. That is a very powerful property of limit. Now the second is, as x gets nearer and nearer to x naught, the values of f of x might not approach any fixed number. That means there can exist there can exist a case when limit x tends to x naught f of x does not exist. There can may happen such a situation. Such a situation can happen, such a situation can happen, such a situation can happen. Okay. In determining limit x tends to x naught f of x, we must consider values of x both on both sides of x naught, from the left as well as right. Left and right, that we said earlier. So also you have to note that sometimes there can be cases where limit x tends to x naught f of x exists, but the function is not defined there. There can exist cases when limit does not exist, though the function is defined. There can exist cases when the limit does not exist and the function there at x naught is not defined. All such cases are possible. Now let's work out example 2. Example 2 gives us a graph which easily makes us understand that we are drawing the graph from here and going like this, and here there is a hole at 2, that means at 2 the function is defined over here, not here. And at 3 there is a break, the function breaks to somewhere, and then again we are moving like this, and here there is a break, and then it goes like this. What the question gives is that we have to find limit t tends to be g of t. So the function given is g of t, and b is given. That means b given is 1, 2, 3, 4, and 5. We have to find limit t tends to 1 g of t, limit t tends to 2 g of t, limit t tends to 3 g of t, limit t tends to 4 g of t, and limit t tends to 5 g of t, which we are going to do. Let's see first when b is equal to 1. That means limit t tends to 1 g of t. That means we are moving from here to here and here to here. That means here the function is moving from here to here, here to here. That means the function is here, right? Which is nothing but 0.5, which is clearly given in the in the figure, right? So this point is 0.5, which is, so the value is 0.5. Now let's look limit t tends to 2 g of t is equal to 1. So we are moving like this, right? From the left we are moving, from the right we are moving towards 2. That means the function is moving like this, right? Function is moving like this, right? So towards where the function is moving, towards here, right? So what is that point? The point is this one, right? This is 0.5, this is 0.1, so this is 1. So the limit t tends to 2, g of 2 is equal to 1, right? But what is g of 2? G of 2 is equal to but 1.5 according to the figure, right? G of 2 is equal to 1.5, but limit t tends to 2, g of t is equal to 1. So that is an observation you get for the second part of the question. Now let's see what is limit t tends to 3g of t. So for that we are moving from the left towards 3, moving from the right towards 3, and the function is moving like this towards here. From the right the function is moving towards there. So can we say that the function is moving towards just one point here? From the left the function is moving towards this point, from the right the function is moving towards this point, so they are different. That means at 3 the function doesn't have a limit. That means limit t tends to 3, g of t does not exist, because for t near 3 g of t has values near 0.5. So from the left when we see, the function is moving towards 0.5, and from the right the function is moving towards 1, so near 1. So there is not a single number approached by g of t as t approaches 3. So we can conclude that the function does not have a limiting value at b is equal to 3. The next one is limit t tends to 4 g of t. So t is from the left and from the right approaching 4. So the function is moving like this. The function is moving like this, right? The function is moving like this, and the function is moving like this. So from the left and right, the function is getting the value. See what is this value? Just this, the value is 1, right? So you get limit t tends to 4, g of t is equal to 1. But you can see that g of 4 is not defined, is not defined here. You can see a hole here, right? Hole. Hole means the function is not defined at that point. That means g of 4 is not defined, but the limiting value at 4 is there, which is 1. So we got limit t tends to 4, g of t is equal to 1, though g of 4 is not defined in this figure. Now the next question is limit t tends to 5, g of t. So we move from the left towards 5, move from the right towards 5. See, and when we are moving like this, it is going up, up, up. Here also it is going up, 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 but it doesn't reach a particular point. It is going like that. The function is moving like that, right? So we cannot find a number from the left and right which coincides. So limit t tends to 5, g of t does not exist. Because as t approaches 5, g of t is growing larger and larger and does not approach any limit from the right as well as from the left. So limit t tends to 5, g of t does not exist. So that's how we solve for those 5 cases of uh, limits that we see in the example. So we are going to move to some of the important properties, basic properties of limits, which you might have already encountered while studying limits. We just give a recap. The first one is, of course, we are assuming that limit x tends to x naught f of x and limit x tends to x naught g of x. Both are existing. Then the sum rule says that limit x tends to x naught f of x plus g of x is equal to limit x tends to x naught f of x plus limit x tends to x naught g of x. That means we can split and sum the limits. The product rule says that limit x tends to x naught f of x into g of x is equal to limit x tends to x naught f of x into limit x tends to x naught g of x. That is also we can just make the product out and then give the limits. Okay. Then the reciprocal rule says that if limit x tends to x naught 1 by f of x is given, that is equal to limit x tends to x naught 1 by x 1 by limit x tends to x naught f of x, provided limit x tends to x naught f of x is not equal to 0. This doesn't happen to be 0, then you can equate it like this. That is called the reciprocal rule. Constant function rule says that limit of a constant function will be always the constant. Identity function, limit x tends to x naught, x is equal to x naught. Replacement rule, if the functions f and g have the same values for all x near x naught, but not necessarily including x is equal to x naught. At x naught, it might be different, but values ev- everywhere else is the same. Then limit x tends to x naught, f of x is equal to limit x tends to x naught, g of x. You can replace f and g. So here the sum and product rules are based on some observations. Like if we have two numbers y1 and y2, uh, we can replace them by the numbers z1 and z2, which are close to y1 and y2. Then z1 and z1 plus z2 and z1 z2 will be obviously close to y1 plus y2 and y1 y2 because they are close as we said earlier. Similarly, the reciprocal rule, how did it come? Like if we have 1 by 14.0001, that will be obviously close to 1 by 14. That is the simple logic behind such things. Constant function rule says that f of x is identically equal to c. Then f of x is near c for all x near x naught. And identity function likewise. You will give an illustration with respect to the constant function c. Suppose if we have a constant function c, this is c, This will be f of x is equal to c, the line f of x is equal to c, or y is equal to c. So everywhere the value will be c. So the limiting value will be always c. And y is equal to x, or f of x is equal to x. F of x is equal to x, or y is equal to x. Here this is f of x is equal to c, or y is equal to c. So when x is moving like that to x naught, the functional value will be moving also to f of x naught, which is x naught. Now let's see example 3. We'll solve example 3 using the basic properties of limits. The first one is to find x square plus limit x tends to 3, x square plus 2x plus 5, x square plus 2x plus 5. How do we do that? Limit x tends to 3, x square plus 2x plus 5. This is a question. So from the basic properties of limits by the sum rule, you can write it as limit x tends to 3, x square plus limit x tends to 3, 2x plus limit x tends to 3, 5. So this is the first question, so we can write it a little more simpler. So this is x into x, right? So for x into x, how can we write? You can write it as limit like this, limit by the product rule, plus here you can write limit x tends to 3, 2 into limit x tends to 3x plus limit x tends to 3, 5. So this is nothing but the identity rule. So you get 3 here, 3 into 3, right, plus 2 constant rule. This is the identity rule plus constant rule. So you get 9 plus 6 plus 5, that is 20. So that's how we find the first one. So the second one is limit x tends to 3, 2x square minus 7x plus 3 divided by x minus 3. So for that, use the quotient rule. Quotient rule says that, and before doing the quotient rule, what you can do, we cannot use the quotient rule. Why we cannot use the quotient rule? Because in the denominator you have limit x tends to 3, x minus 3, which will be 0. So you cannot use the quotient rule. We have to make it non-zero if we have to use quotient rule. So when we don't take x is equal to 3, we earlier said that you can factorize the numerator and cancel out x minus 3. When x not equal to 3, then you get x 2x minus 1, right? So with the replacement rule, you just take f of x is equal to this and gx is equal to this. Okay, since this functions agree for x not equal to 3, you can say that you can replace. That means we know that f of x is equal to g of x everywhere except at x is equal to 3. So this happens to be the usage of the replacement rule, which was the last one in the basic properties. So instead of this function, you can use 2x minus 1 here and then use the sum rule, constant rule and the product rule together to get it as 5. So what's the third question? Is to find limit u tends to 2, 8 u squared plus 2 divided by u minus 1. So the question is very simple. 8 u square 8 u square plus 2 divided by u minus 1. 8 u square 8 u square plus 2 divided by u minus 1, where limit u is tending to 2. So this is the question. So when u minus, okay, so the you can just apply this is u minus 1, so you can find the limiting values of numerator and denominator separately and use the quotient rule, because we know that the limit of the denominator is not going to be 0 because that will be 1. Okay, calculate and find it out, and the answer will be 34. And also we can extend our basic properties of limits to n numbers. Earlier we said if we have f of x and g of x, you can just extend it to n functions, f1 of x plus etc plus fn of x, and then we can split the limits, and that's called the extended sum rule. And also we can extend the product rule, the constant rule can be extended as constant multiple rule. That means limit c into f of x is equal to c into limit f of x. And then the quotient rule, the same. The power rule is limit x tends to x naught x raised to n, can be calculated as x naught raised to n, where this x naught is not equal to 0, and that will be the derived properties of limits, which are nothing but induction applied on the basic properties of limits. So let's see example 4 and wind up this lecture. The example 4 says to find limit x tends to 1 x cubed minus 3x square plus 14x divided by x raised to 6 plus x cubed plus 2. Uh, Calculate it using the basic properties of limits, the quotient rule, the sum rule. Use all such rules which can be applied here, and you get the value to be 3. This is very simple to find out the limits of uh, functions, such simple functions. So that's all for this video lecture. Thank you for watching out, and please work out and lecture down the points which we mentioned. Thank you.